post-quantum cryptography. Introduction. In a world where quantum computers are poised to break today's encryption standards, the future of data security is at a crossroads. How can we protect our digital world in the post-quantum era? Join us as we explore the revolutionary field of post-quantum cryptography and discover the cutting-edge techniques that will safeguard our future. Stay tuned at Tech Revolution. Understanding quantum computing, basics of quantum mechanics. Quantum mechanics is the branch of physics that deals with the behavior of particles at the smallest scales. Unlike classical physics, which describes the world in terms of definite states and trajectories, quantum mechanics introduces concepts like superposition and entanglement, where particles can exist in multiple states simultaneously and be instantaneously connected regardless of distance. How quantum computers work. Quantum computers leverage the principles of quantum mechanics to perform computations in ways that classical computers cannot. Instead of using bits that represent 0 or 1, quantum computers use qubits, which can represent both 0 and 1 simultaneously due to superposition. This allows quantum computers to process vast amounts of data in parallel, solving complex problems much faster than classical computers. Potential applications of quantum computing. The potential applications of quantum computing are vast and varied. They include solving complex optimization problems, simulating molecular and chemical processes for drug discovery, advancing artificial intelligence, and breaking traditional cryptographic codes. Which brings us to the need for post-quantum cryptography. The threat of quantum computing to current cryptography. Current cryptographic methods, today's cryptographic systems such as RSA and ECC, rely on the difficulty of certain mathematical problems, like factoring large numbers or computing discrete logarithms. These problems are considered practically unsolvable for classical computers, ensuring the security of encrypted data. How quantum computers can break traditional encryption. Quantum computers can solve these cryptographic problems efficiently using algorithms like Shor's algorithm, which can factor large numbers exponentially faster than the best-known classical algorithms. This capability threatens the security of traditional cryptographic methods, making it possible to decrypt sensitive information that was previously considered secure. The urgency for post-quantum cryptography as the development of quantum computers progresses. The urgency for post-quantum cryptography becomes clear. Organizations and governments must prepare for the transition to quantum-resistant algorithms to ensure the continued security of their data and communications. Introduction to post-quantum cryptography. What is post-quantum cryptography? Post-quantum cryptography refers to cryptographic algorithms designed to be secure against the capabilities of quantum computers. These algorithms aim to provide the same level of security as current cryptographic methods, even in the face of quantum computing threats. Key principles and goals. The key principles of post-quantum cryptography include ensuring confidentiality, integrity, and authenticity of data. The goals are to develop algorithms that are not only resistant to quantum attacks, but also practical to implement and compatible with existing systems. Differences from traditional cryptography. While traditional cryptographic algorithms rely on problems like integer factorization and discrete logarithms, post-quantum cryptographic algorithms are based on different mathematical foundations, such as lattice problems, code-based problems, and multivariate polynomial problems. Quantum-resistant algorithms. Overview of lattice-based cryptography. Lattice-based cryptography uses the hardness of lattice problems, such as the learning with errors LWE problem, to create secure DAO. Encryption schemes. These problems are believed to be resistant to both classical and quantum attacks, making them a promising candidate for post-quantum cryptography. Code-based cryptography relies on the difficulty of decoding random linear codes. The most well-known code-based crypto system is the MC Elise crypto system, which has withstood cryptographic attacks for decades and is considered quantum-resistant. Multivariate polynomial cryptography involves creating cryptographic schemes based on the difficulty of solving systems of multivariate polynomial equations. These problems are considered hard for both classical and quantum computers, providing a strong basis for secure encryption. Hash-based cryptography uses cryptographic hash functions to create secure digital signatures and other cryptographic primitives. Hash-based signatures, such as the Merkle signature scheme, are known for their simplicity and security against quantum attacks. Real-world applications and implementation. Securing communications and data post-quantum cryptography is essential for securing communications and data in a quantum future. This includes protecting emails, messages, and data stored in the cloud from quantum attacks. Protecting financial transactions. Financial institutions rely heavily on cryptography to secure transactions and protect sensitive information. Implementing post-quantum cryptographic algorithms will ensure the continued security of online banking, credit card transactions, and financial exchanges. Ensuring the integrity of critical infrastructure. Critical infrastructure, such as power grids, transportation systems, and healthcare networks, must be protected from cyber attacks. Post-quantum cryptography provides the necessary security measures to safeguard these vital systems against future quantum threats. Post-quantum cryptography in blockchain and cryptocurrencies. Blockchain technology and cryptocurrencies depend on cryptographic algorithms for secure transactions and data integrity. Transitioning to post-quantum cryptographic methods will protect these technologies from the capabilities of quantum computers. Challenges and limitations. Technical challenges in developing quantum-resistant algorithms. Developing quantum-resistant algorithms presents several technical challenges, including ensuring their security, efficiency, and compatibility with existing systems. Researchers must address these challenges to create practical and secure post-quantum cryptographic solutions. Implementation challenges in existing systems. Implementing post-quantum cryptographic algorithms in existing systems requires significant effort, including updating software, hardware, and protocols. Organizations must plan and execute these transitions carefully to maintain security and functionality. Compatibility and interoperability issues. Ensuring compatibility and interoperability between post-quantum cryptographic algorithms and existing systems is crucial. Standardization efforts and collaborative initiatives are essential to address these issues and promote the widespread adoption of quantum-resistant encryption. Current research developments. Leading organizations and researchers in post-quantum cryptography. Several organizations and researchers are leading the charge in post-quantum cryptography, including NIST, ESO, and various academic institutions. Their efforts focus on developing, testing, and standardizing quantum-resistant algorithms. Recent advancements and breakthroughs. Recent advancements in post-quantum cryptography include the development of new quantum-resistant algorithms, improved security proofs, and practical implementations. These breakthroughs are essential for building a secure quantum future. Preparing for the post-quantum era. Strategies for organizations and governments. Organizations and governments must develop strategies to transition to post-quantum cryptography. This includes assessing current cryptographic systems, identifying vulnerabilities, and implementing quantum-resistant algorithms. The role of standardization bodies. NIST, ISO standardization bodies like NIST and ISO play a crucial role in the development and adoption of post-quantum cryptography. Their efforts ensure that quantum-resistant algorithms are secure, efficient, and widely accepted. Ethical and legal considerations. Balancing security and privacy post-quantum cryptography must balance the need for security with the protection of individual privacy. Ensuring that quantum-resistant algorithms do not infringe on privacy rights is essential for maintaining public trust. Regulatory and compliance issues. Regulatory and compliance issues must be addressed to ensure the widespread adoption of post-quantum cryptography. Governments and organizations must develop policies and regulations that promote the use of quantum-resistant encryption while maintaining security and privacy standards. Future prospects and innovations, predictions for the next decade. In the next decade, post-quantum cryptography will become increasingly important as quantum computing technology advances. Predictions include the widespread adoption of quantum-resistant algorithms, new breakthroughs in cryptographic research, and the development of more efficient and secure post-quantum methods. Conclusion. In conclusion, post-quantum cryptography is a critical field in ensuring the security of our digital world in the face of advancing quantum computing technology. By understanding quantum computing, the threats it poses, and the strategies for developing and implementing quantum-resistant algorithms, we can protect our data and communications in the post-quantum era. Stay informed and engaged with Tech Revolution as we continue to explore the frontiers of technology.